Well, that might render something like this, where we can see a little bit of the circle shining through the square and then also background everywhere. So opacity was applied to the circle and the square separately. But contrast that with this, where opacity now starts to play that role of parentheses in math and elevating the prominence of this certain relationship. And what this will do is require that the circle and the square be fully composited together, which in like Photoshop would be like right-clicking and rasterize this layer before any opacity is applied. And this will render something different, where we still see the background showing through the whole time. So opacity has obviously been applied to everything, but those pixels of the circle are not able to shine through the square, even though its opacity was reduced, because they were fully composited together before opacity was applied, and yet that information was lost. Now, this is not something that everyday Flutter developers have to think about at all, but this is the kind of stuff that the framework authors needed to get right to support every UI that we might dream up. All right, good morning, everybody. Welcome to Flutter Heroes. My name is Craig Labenz, as you just heard, and today I'm going to continue a talk that I first started at Flutter Vikings in the fall, I think it was, of 2022. That was called the life cycle of a widget. This is just going to pick up where that left off. It's the life cycle of a render object. Now, that talk was about more than just widgets, of course, because widgets are these lifeless configuration objects. We all know this. They don't change. Just like your X, they never update, and they have no life cycle. So just like that talk was about more than widgets, this talk will also be about more than render objects. Now, there's a lot to get through here, but I do want to have a quick recap of some of the highlights of the life cycle of a widget so we can all make sure we have the same starting point. So first, Flutter either builds or rebuilds your widget tree. It syncs it to the element tree, and then every render object widget has its create render object method called, and that yields the render tree. And at that point, Flutter is finally ready to start drawing some stuff. Now, I'm not going to spend a lot of time here talking about how to write your own custom render object. If that topic interests you, then check out the first episode of the Flutter Build show on writing custom render objects. Okay, so let's get to know this darn thing. I'm going to build up a graphic of the life cycle of a render object, starting with this artistic gem. And the white blob on the left is always going to show the outside actor or the force that has spurred our render object into motion. And then on the right in blue is going to be the actual life cycle as we're building it up. Oh, I did want to say one more thing here, which is that for this first phase, the render object widget that is behind this render object has its create render object method called, as we said, and that brings our render object into life, and we're ready to get started. So the first thing to know about the render object class is that it is an abstract class, and it's actually fairly unopinionated. It does inherit some basic tree-related mechanics from its parent abstract node, and then beyond that, it just gets started setting up a few of its own concepts. And the first concept is layout. And you can think of layout as a render object both sizing itself and then asking all of its children to size themselves within whatever constraints that render object implies. And this is where that Flutter adage that constraints go down, size comes up, parent sets position comes from. So that brings us here in the life cycle of a widget for this kind of meta phase that I basically call the flush phase. It's not its official name or anything. But this happens when the pipeline owner calls its various flush methods. And the pipeline owner is a very high-level class that kind of runs the whole show. I talked about that more in life cycle of a widget as well. Okay, so there's a couple of methods that come together to comprise layout, and they are layout, which is implemented by the framework, and it's called by that pipeline owner, and it recurses down through any ancestor render objects until it reaches us, whatever render object we are. And then the second method is called perform layout. Now, layout is mostly just bookkeeping, and it doesn't really do any actual layout work itself. It delegates to perform layout, which is the method that we implement. And then the final method that brings together all of layout is this method mark needs layout. And this is how we tell if you are writing a render object, which you needn't ever do, but this tells the framework that the given render object is ready to be re-laid out. Now, the reason that the layout signature returns void instead of any sizing information is that this allows descendant classes of RenderObject to have radically different layout protocols. So by far the most common of these descendants is called RenderBox, and that just assumes that you want Cartesian coordinates or standard XY coordinates. So for RenderBox, the job of perform layout is to figure out how much space that piece of the UI is going to require, and then save that information in the size attribute. So here's an example of the padding widgets render object called render padding. And we can see here that we've got the perform layout method. There's tons of bookkeeping stripped out of here. In fact, all code samples in this talk will just have enormous amounts of tedious bookkeeping that the framework does all stripped out. But it ultimately calls perform layout. And then in perform layout, it asks its child to lay out, and then uses that information to determine its own size. And we can see the adage happening right there. The constraints are going down to the child. The size of the child is coming back up. That's being used to determine this render object's own size. Now, we're not seeing the parent setting the position part here, because that happens in painting. And painting is the most render object-y thing a render object could ever do. And for painting, we stay in this kind of meta flush phase from the pipeline owner's perspective. And similar to layout, for the first frame, every single render object has to paint, but then on subsequent frames, only render objects that have had something change will need to repaint. So there's two top-level methods that come together to comprise painting. And they are paint, which is implemented by us, and just like layout, recurses all the way down from the pipeline owner until it reaches us. And this method actually just does all the actual work. There's no kind of bookkeeping wrapper like we had with layout and perform layout. The second method is mark needs paint, which is the analog to mark needs layout. And this is called by us to tell the framework that a given render object needs to repaint. Now there's a gotcha here, which is that the concept of layout completely implies needing to paint or repaint. And this makes sense because if the size that a render object is going to ultimately fill changes, then of course the pixel buffer that it will need to ultimately produce will have to change as well. So anytime you tell a render object that it has to lay out, it will also repaint itself. Okay, so this paint method takes a couple of interesting parameters. We see this painting context there and an offset. So the offset is our position, the origin of our render object relative to the origin of our parent. And we just got done laying ourselves out as a render object. So you might think that now in the paint phase, we can actually only draw within the lines that we've indicated by that size value we set during layout. But that is actually not a constraint that render objects live under. Any render object can draw anywhere on the screen. And it'd be very chaotic to draw very far outside of your bounds. But this not being a restriction is very valuable for render objects. It makes the implementations for drop shadows, glow effects, anything like that, a lot more simple to implement. So render objects do not have to color within the lines. Now what about this painting context thing? What is that? Well, if you've ever written or read render object code before, or written a custom painter, you might have seen lines of code like this, context.canvas, draw rect, draw circle, draw line, there's all these methods. And they suggest that before we could ever really know what this context thing is, we may need to understand what a canvas is. So the canvas class's docstring opens with the line, an interface for recording graphical operations. And it's modeled after a real-world canvas, but it's quite different. Because if you stand in front of a real-world canvas and paint on it, actual fibers on the canvas get covered in paint, and their color changes. And the equivalent in Flutter would be when something finally starts to produce a buffer of RGBA values to assign color values to individual pixels. But this canvas class does not do that. It just stores graphical operations, and then how they're going to play out, how they're going to resolve, what will ultimately be produced is yet to be seen. So going back to the painting canvas, or painting context, sorry, that object manages canvases. And it has a default one that's found at context.canvas, but you can also create more canvases or these other objects called layers, and we're going to spend a lot more time on layers in the second half of this talk. Okay, next up in the life cycle of a render object is semantics. And I'm excited that there is an accessibility talk later in the day because accessibility and semantics are just best friends. Flutter's semantics system is very important because it integrates with screen readers and other accessibility tools of whatever the host operating system is or the web browser if you're running Flutter in a web environment. So that wraps up the flush kind of meta phase, again, from the pipeline owner's perspective. Layout, painting, and semantics kind of all happen in rapid succession, one after another. And there's two top-level methods that come together to comprise semantics. And they are describe semantics configuration, which really rolls off the tongue, and mark needs semantics update. And semantics in Flutter warrants its own deep dive entirely, but this is how describe semantics configuration works. It accepts this semantics configuration object, which is a mutable object, and it's the job of the render object to kind of staple onto it any necessary information. Now, Flutter sets us up here for success by offering the widget library, and those all produce render objects that tend to these details. And so Flutter aims to kind of just work from an accessibility perspective right out of the box. But as I'm sure the accessibility talk later will highlight, it is very important for us as app developers to test our apps with accessibility tools turned on to make sure that there are no awkward surprises and that users of our apps who depend on those technologies can actually complete the tasks that they set out to do in our apps. Because often, sadly, there will be awkward surprises despite Flutter's best efforts. Okay, now all of the above is sufficient to draw one frame, but I alluded earlier to the fact that not all of that code will need to rerun on every subsequent frame. And render objects in particular have a very structured way of determining whether or not they can reuse old values or if they need to recompute fresh values. Let's take a look at how that works. We saw these three methods: mark needs layout, mark needs paint, and mark needs semantics configuration. And I don't know who mark is, but apparently needs a lot of things. But they all correspond to these other primary methods: layout, paint, and describe semantics configuration. So to walk through this, we're going to pretend that we're writing just a sliver of actually it's funny, sliver is a loaded term in Flutter, just a slice of a render object, and all this class is going to do is accept and display a single string, and so we're going to call it render string. Now, the way this works is you take the value that was passed in and store it on a private variable on the render object. And then you get to work writing a setter that looks like this. And within the setter, the first thing you want to do is short circuit if the value that was supplied is not actually new. But then if it is new, things start to get interesting. So you store the value, of course, on the private variable. And then it's time for the render object author to call the correct mark needs methods. Now, this render object just got a new string. So it needs to call mark needs paint. If it doesn't do that, it'll continue to show the old letters, the old characters of the old string. So we have to call mark needs paint. But the new string may also take up a different amount of space. And the only way that we can determine if it even does take up a different amount of space is to call mark needs layout. So we have to call mark needs layout. But aha, the observant viewer says, mark needs layout implies mark needs paint. And that is true. So we can remove the spot where we called mark needs paint. It is completely redundant and unnecessary to actually call. And then the last thing is that a screen reader is probably going to have to be able to say aloud whatever this string value is. So we also need to call mark needs semantics update. And again, for more on all of this stuff, check out that first episode of the Flutter Build show on writing your own custom render object. Okay, now within these mark needs methods, like what do they do? Well, here's the pseudocode for mark needs layout, again, with lots and lots of bookkeeping stripped out. The main thing that this method does is first bubble up the render tree and mark every single render object it finds as also dirty until it hits a layer boundary. So we're seeing a little bit more about layers. Again, they're to come later in the talk. Then the next thing it does is mark itself, and of course this happens recursively going up the tree, mark itself as dirty, and it puts itself in the queue for the pipeline owner's next flush phase. Okay, and then what code triggers this magic setter that we've been looking at? Well, remember, you have render objects, and they're long-lived, but then widgets are coming and going every frame if something is different. And so let's say you've got a new widget with some value, because you called set state somewhere. The long-lived render object is sitting there. The element tree is conducting all of this, of course, and the new widget is plopped in, and then the element tree passes that render object into the update render object method of the new render object widget. And we can see here in that method, the render object is being passed in to the brand new widget, and this line is where the widget just very simply plops all of its values right on the render object, and that .value property is the magic setter that we've been writing. So if the value is new, then all of the machinery kicks into place and Flutter is ready to update. So that brings us here in the life cycle of a render object, where this widget.updateRenderObject method can lead to a render object marking itself as needy, so to speak, and then that can queue that render object in the pipeline owner's next flush phase. Things are getting exciting. Now, the next role of render objects is to support hit testing. And it was always going to have to be render objects that supported hit testing, because the whole concept of hit testing is that a user is interacting with their screen in some way, their finger or mouse or something. So the operating system gets coordinates where this event took place, and then it asks the Flutter engine what's going on there. Or, well, it actually just tells the Flutter engine, hey, there was an interaction at these coordinates. And then the Flutter engine asks the Flutter framework, like, hey, what's at those coordinates? And within the Flutter framework, only render objects know anything about their size or their location, and so only they could ever answer this question. So the hit test method looks like this. And it first accepts this box hit test result object, to which it will append hit test entries. And it also accepts an offset. And now this, an interesting note here is that hit testing is implemented on render box and not on render object, because hit testing implies some concept of coordinates, and render box has a concept of coordinates, but render object knows nothing about that. So if you ever subclass render object yourself, then you will be on the hook to implement hit testing, but in practice, very few people do this. Now, back to the method. The first thing it does is short circuit if the position is deemed to be outside the bounds of the size that was established during layout. So render objects can color outside the lines during the paint phase, but they do not accept hit test results from outside of their bounds. So you could touch on like the glow effect of, or the drop shadow of something that has a hit test, or that has a gesture detector in it, and you'll have probably seen, if you've done that test, that Flutter does not register that hit test. So then the next thing that it does is ask all of its children if they care about this hit test, and it even asks itself, because a lot of render objects just don't care about hit testing. Like, think about the render padding class that we saw earlier. That's just a positioning widget. Like, maybe its children care about hit testing, but render padding definitely doesn't. And so that hit test self method that we see there just returns false for actually most render objects. But eventually, that result list is built up, and then that goes into the arena, and that's a whole other system. But that brings us here in the lifecycle of a render object, where a user gesture can lead to a positive hit test result. That can lead to a callback on something like a gesture detector being fired, which could lead to set state being called. That leads to widget.updateRenderObject being called, and that render object is passed in. The render object can mark itself needy, and then it's back in the queue of the pipeline owner's next flush phase. Nope, that's the wrong arrow. I do this every talk at least once. Now, all good things do come to an end, and so eventually this render object too shall pass. There's no real surprises in the Dispose method. It looks just like what you'd write on a state class for a stateful widget. If you create a layer or a text painter, then you need to clean those up, just like if you created a text editing controller or an animation controller or anything like that. And so that concludes the life cycle of a render object. But oh boy, does it not conclude this talk. The next thing is kind of outside the life cycle, so to speak, of a render object, but I think it's still interesting and important. And it's this optional field on render objects called ParentData. And when used, it's mostly set and read by the parent. And I remember the first time I saw this variable in code, it was very unclear to me, like, is this from the parent or for the parent? Like, what is this thing? But here's an example of this for the RenderFlex render object, and this sits behind column and row. And we can see here that the RenderFlex object is using ParentData to cache the order of its children. And then more generically, render objects will often use ParentData to store their children's layout and sizing information, anything like that. So I think of ParentData as like, if you had a parent that was just really kind of lazy and absent and couldn't even be bothered to learn their children's name. So imagine like Homer Simpson made Bart and Lisa wear t-shirts with their names on them because he couldn't be bothered to figure out which one was which. So in this scenario, the t-shirt that Bart is wearing would be the ParentData, and then the letters that say Bart are the specific information that Homer has put on the ParentData. So not very good parenting happening in Flutter's render tree. Now there's other widgets that make very explicit and concrete use of ParentData. If you've ever wondered how a positioned widget knows to complain if you use it outside of a stack, despite the fact that widgets are not supposed to have any opinions about their ancestors, descendants, or siblings, well, this is how, because the render object behind the positioned widget takes a peek at its ParentData, which is normally only set and read by the parent, but it takes a peek at that and makes sure that it both exists and was set by a stack. And if either of those things are untrue, then it throws an exception. Okay, so that is now a pretty high-level overview of a render object. But there's a big gap in the story, if we were to leave it here, because we are not close to anything having assigned color values to every pixel on the screen. So we must plug on. Oh yeah, okay. So, to recap, we have the element tree, which offers a declarative API for us to describe how our UI works. Then we have the element tree, which syncs changes from one frame to the next. It delivers the imperative code to do all of that. And then behind both of those, we have the render object tree, which stores graphical drawing instructions and layout and sizing information. But eventually, something is going to have to actually evaluate those drawing instructions, or our apps will never show anything. So to that end, I would like to introduce you to the layer tree. Now, you would have been excused for thinking that the render tree rendered stuff, but it turns out, no. So once the render tree has finished recursively calling paint, then the context object is left holding on to any and all canvases that the render objects collectively created and wrote painting instructions to. And each render object could have written to that default canvas that was found at context.canvas, or it could have created another one in the form of adding a layer to the layer tree. So if this operation never happens, then the layer tree will just have one node, and it's that canvas found at context.canvas. But every time a render tree does something clever like this, then the layer tree grows. And the layer tree, when appropriately used, is a big performance win, but when inappropriately used, is a big performance hog. So one takeaway that you should not have from this talk is, I need to go home and start writing more render objects and like aggressively make my own layers. Like, do not do that. Okay, now, there are two cool things that layers do. The first one is figure out when one render object marks itself as dirty, how many of its neighbors will also have to repaint. So here is a visualization of a hypothetical layer tree superimposed over the render tree that created it. And let's imagine that this render object was marked dirty for whatever reason. Its widget had set state called on it. And instead now of bubbling all the way up to the root of the render tree and thereby dirtying the entire tree, because of course all descendants will have to repaint when any one render object does, it will only bubble up to the top of the layer. So it kind of quarantines that repaint signal and holds it in place. And this happens because of the layer check that we saw in the method like markNeedsLayout. So it's bubbling up there and it stops when it gets to a parent that's not in the same layer. And again, this is pseudocode. I don't think there's even a setter, or I don't think there's even a property called isSameLayer, but it's like a bunch of code to deduce essentially this. So the second thing that layers do is kind of behave like parentheses in math. And we all know that mathematical operations are resolved according to the order of operations, but parentheses can mix that up by changing a math equation entirely. They can disambiguate, or they can change something entirely by elevating the prominence of certain relationships. And in Flutter UI, layers can perform this same role. So let's imagine some Flutter layout written a little bit more like grade school math. Here we've got a background and then a circle and a square, each with some opacity applied to them. Well, that might render something like this, where we can see a little bit of the circle shining through the square and then also background everywhere. So opacity was applied to the circle and the square separately. But contrast that with this, where opacity now starts to play that role of parentheses in math and elevating the prominence of this certain relationship. And what this will do is require that the circle and the square be fully composited together, which in like Photoshop would be like right-clicking and rasterize this layer before any opacity is applied. And this will render something different, where we still see the background showing through the whole time. So opacity has obviously been applied to everything, but those pixels of the circle are not able to shine through the square, even though its opacity was reduced, because they were fully composited together before opacity was applied, and yet that information was lost. Now, this is not something that everyday Flutter developers have to think about at all. Even if you're writing your own render object, it's very rare that you'll need new layers, but this is the kind of stuff that the framework authors needed to get right to support every UI that we might dream up. And like I said earlier, needing layers is extremely rare. It's mostly used when a render object either doesn't trust its children to not screw up a canvas in some way, or it needs all of its children to conform to the same transform or clip or something like that. And this implies also that if you're ever writing a leaf render object, you definitely don't need a layer because you don't have any children. So that's the two primary jobs of layers. To divide render objects into these smaller subcomponents that will all repaint together, and to act like parentheses in math and potentially elevate certain relationships. So, zooming all the way out, here is some very high-level code at the very beginning of Flutter that drives this whole process. It's the widgets Flutter binding class with the render binding mixin. And in this draw frame method, we first see the pipeline owner that we've been talking about goes through its flush phase. And again, it's actually, I think, 5 methods, if I remember right, that flush all the different parts of the widget element and render trees one at a time. But that wouldn't fit on the slide, so I'm just calling it flush. Now this forces all the render objects to update everything, and then when they're done, that yields the layer tree. And then this scene builder class takes the layer tree and turns it into a thing called a scene. Now, this all happens in the Flutter engine, so it's pretty opaque to the Flutter framework. But the scene object that is returned is basically a list of drawing commands and the hand-selected shaders that can satisfy those drawing commands. And then there's a class from Dart UI called Flutter View that takes that scene and actually renders it by shipping it off to the GPU and graphics drivers. Now, this method, draw frame, if you remember from Lifecycle of a Widget, if you've seen that talk, there was this concept of a persistent callback, which is a method that Flutter will run every time it draws a new frame. So the operating system has a vsync signal, it sends it to the engine. The engine's like, great, cool, framework, it's time for a frame. And all the framework does is run all of its persistent callbacks. Well, this all-important method, draw frame, is thankfully one such method. You can add your own next to this if you want. And then in here, this task of translating that layer tree into the scene, which was the list of drawing commands and the hand-selected shaders that can compute color values for every pixel, this is an incredibly complicated task and a ton of work. And in the second episode of the Flutter Build show about writing custom shaders, I said that Flutter was on easy street if you do supply your own shader, because it gets to skip a lot of work. And this is that work that Flutter gets to skip if you supply your own shader. And then lastly, this line down here, view.render, this is where Skia, or now increasingly Impeller, are hiding. Okay, teleport yourself onto the GPU. You are the graphics driver, and you've just gotten 3 shaders from Flutter that you need to execute. We've got A, B, and C. So you run all of those shaders, and let's say they produce these outputs. Shader A is creating 3 gradients that are reducing in opacity from left to right. Shader B is rendering a diagonal green line, and shader C must be our background because it's all white pixels. So what needs to happen now is that these 3 pixel buffers need to get composited into a single pixel buffer to actually show on the screen. So it just moves down the line, blending these with the blend mode that you would expect, kind of the default one in Photoshop again. And let's quickly walk through how that works. So for that 0, 0 index, the very first pixel, the red value from A had full opacity, so it completely obscures the green and the white below it, and we just get a red pixel. And then it moves down the line, and these red pixels had some reduced opacity, so a little bit of white is showing through there, a little lighter in the result buffer than they were just straight out of shader A. And it keeps going, and like this second pixel in shader A had some reduced opacity in the orange, so some green shows through, and we get this nice mud water color. It's really pretty. So it keeps going. You get a little green showing through this blue, and ultimately we finally get the actual UI that your widgets were originally describing, and this can be sent back to the operating system, and finally, Flutter will show some darn pixels on your device's screen. We did it. We rendered something. Now, there are a few edge cases that I want to talk through that me exploring really helped me understand. All of this stuff. So, first of all, what happens when nothing is happening? Let's say you run flutter.run, and your app, whatever you're working on, launches on whatever device or emulator you're using, and then you think, wait a minute, it's Saturday morning, what am I doing? And you go outside. Well, the device is still sending vsync events to Flutter every few milliseconds. So is Flutter doing all of this work every time while it's just sitting there? And that answer is no. So when the vsync signal arrives from the operating system, if nothing has changed in your app, then the engine will just reuse the previous pixel buffer, and it's a clean no-op for Flutter. And then what happens on the graphics driver actually differs by device. A lot of devices will just not try to get cute and completely replace the old pixel buffer with the exact copy of it. Some devices try to get cute, and then they can be buggy, and caching is hard. Okay, question number 2. What's up with repaint boundaries? Well, we talked about layers earlier and mentioned how layers serve to quarantine repaint signals as they bubble up the render tree. Well, the Repaint Boundary widget exists to do one thing, and that is insert a layer into the layer tree. So let's pretend that this layer exists because of a Repaint Boundary widget. Any render object could have added this in its paint method, but we're just going to pretend that the reason that this one exists was a Repaint Boundary widget. So just like we saw before, this will quarantine the spreading repaint signal. There's nothing special about the layer added by a repaint boundary. It's just another layer. So you might be thinking well, that seems kind of anticlimactic. Why does this render repaint boundary widget exist? Well, Flutter's goal is to almost never make developers dip below the widget layer. Yet we're reusing the word layer. This layer concept is important and valuable. So the Repaint Boundary widget exists to expose this very low-level rendering mechanic all the way up to the widget's layer. Now, it's possible for both sides of any layer boundary to still re-render at the same time, but only if they both wanted to for their own separate reasons. Note that when this happens, that extra layer still in the Flutter framework paid the cost of the extra compositing work that it had to do when it was building the scene and all that stuff, but it was all for naught because both sides of the layer were rendering anyway. Now, this means that extra layers are great when they're appropriate and expensive when they're inappropriate. So they're kind of risky. But there is one scenario where the Flutter framework is so sure that a repaint boundary is probably useful that by default it adds one around every one of something. Does anyone have any guesses what scenario is so conducive to a repaint boundary that one is added by default? It's okay, I'll just tell you. The answer is if the items are scrolling, because then the framework has a really high confidence that it is about to draw the exact same pixel buffer at a slightly different offset. So imagine you've got a phone, and you're just kind of scrolling on a list view, and all the list tiles are sliding up, right? That repaint boundary is being caught by the list view, the repaint signal is being caught by the list view, but then all of the tiles are able to not repaint themselves as they're moving up because they're all wrapped in a repaint boundary within the list view widgets build method. But there are even gotchas here because there's a scenario that can undermine the repaint boundary's usefulness even in the scrolling items scenario. I'm going to try again. Any guesses? Oh, wait. Someone actually did say something. What was that? I can't hear you. I'm sorry. Shrink wrap. Oh, shrink. That's a great guess. It doesn't relate to this one too much. That basically removes the laziness of a list view. The answer here is if the scrolling item is animating, because then not only does the layer tree get way bigger, because every list item adds a new layer, but as you're scrolling and the list view was collecting that gesture and sending a repaint signal to its render object, all of the descendant items are repainting themselves anyway, assuming they all have some animation going on. So repaint boundaries really are tricky to use correctly. The list view also has a parameter for whether or not it should even add these. So if you know in your list view all the tiles are animating as they're moving or just they have some kind of ambient life to them, then it's good to turn that off. Now, no one would ever write code like this, but this is an example of a perfectly wasteful repaint boundary. We've got a gesture detector that sets some state, this my color value, and then there's two color boxes separated by a repaint boundary. Well, the problem is both of those colored boxes use the same my color variable. So they're definitely repainting at the same time, meaning that this repaint boundary is perfectly wasteful. Now, this example is super contrived, but what about real scenarios? Like, how do you actually figure out if you should use a repaint boundary? The short answer is it's pretty tricky and just always default to not using one. But the better answer is that DevTools is here to try and help. So if you navigate to a specific repaint boundary in DevTools, you'll see this diagnosis property that has, in just plain language, how the framework thinks that render object is performing. And right above it is the metrics property that is the raw data behind the sentence. And so in this scenario that I took a screenshot of, there had been 150 repaints, and one time both the repaint boundary's descendants and ancestors repainted. And then 149 times, only one of them repainted, and it doesn't discriminate about which one it was. So that's a hit rate of 149 out of 50, obviously, quite good. And if you can read the sentence, the framework is telling us that it thinks this is a super useful repaint boundary and that we should probably keep it. Okay, next. What does all of this mean for performance profiling? Well, for most frames, in most situations, your time expenditure is probably going to look something like this. So assume you've got 16 milliseconds for this hypothetical. That gets you 60 frames per second. Your UI thread is going to finish pretty quickly, generally speaking. And the UI thread is where all Dart code runs. So that's the entire Flutter framework and any application code that we write. Widget build methods, state management code, all of it. That's in the UI thread. Dart is sufficiently fast at creating and disposing of small classes like widgets, text styles, our own state management things, like all that stuff. So if you open DevTools, you'll often see that the UI thread wraps up quite quickly. And then it passes the baton to the raster thread. This happens in the Flutter engine, and this is where the layer tree is converted into a scene, and then the scene itself is ultimately passed to Skia, or now Impeller. And you can see, and obviously I've just made up these hypothetical values of 2 and 8 milliseconds, but they're fairly representative of times that I've looked in the DevTools. the raster thread takes way longer. And then if you've got extra time, the Dart VM loves to sneak in a quick garbage collection. Some folks will see regular garbage collections in DevTools and think, oh my gosh, like, am I creating too many objects? Am I not cleaning things up? Like, is this causing a performance hit? And actually, seeing regular garbage collections in DevTools probably just means that all of your frames are coming in under budget. So that's a good thing. Now, let's think about what this means in terms of writing a Flutter app. Flutter developers, all of us, myself included, spend a lot of time hyper-optimizing every last detail of a build method. Like, oh, is that widget rebuilding when it didn't strictly need to? And am I using const everywhere? But like, imagine what happens. Let's say you've got a widget tree that's all const widgets, and then there's one widget that changes. This is a fairly unrealistic widget tree, but bear with me. Think about what happens in everything that we've just talked about in this scenario. Well, the render object, let's say it was like a favorite icon in this whole page, and the user tapped the heart outline and it fills in. So what happens behind this? Well, that render object marks itself as dirty, and it bubbles up to whatever is in its own layer, and that could be the whole screen or it could be contained. And then what happens next? Well, the render tree repaints, and we get a new layer tree, which is either largely the same or different. But that layer tree then has to go into the scene builder to be turned into a scene. And that was on the raster thread. That's what's taking a lot of the 8 milliseconds. So that runs for way longer. And all of the work happens again anyway, even though we were surrounded by const widgets. And then that scene has to go to Impeller, and all the shaders are run, and they all produce a pixel buffer. And those pixel buffers are all collapsed down in the compositing step to the final pixel buffer. And all of that work, again, happens regardless of whether or not our little heart icon was surrounded by sufficiently separated widgets that were const or not. So that doesn't really matter. We're only really tweaking what happens in the 2 milliseconds of the UI thread, and then the raster thread has to do all of its work anyway. And this is partly a design decision of Impeller. It didn't used to quite be this way with Skia, but caching is hard, as we all know, and Impeller has a goal to always be fast enough to render frames under budget without ever needing to make use of raster caching, which would basically be the pixel buffer of a certain part of the UI from the previous frame. So, for more info on all of this stuff, if you found any of it interesting, I invite you to watch this old talk. It's actually 8 years old now. I took the screenshot about a year ago. But this was, this is from some of the original developers that broke ground on the early Flutter code. And a lot of the info here is still very, very accurate. Really, the only thing that has changed, they do spend a bit of time talking about that raster caching that was extremely valuable in Skia, and Impeller doesn't do any of that anymore. So if you watch this talk, whenever they mention raster caching, you can just go to sleep. But the rest of the talk is very valuable. And then lastly, special thanks to these 3 guys, Dan Field, Jonah Williams. They're on the Flutter engine team. Michael Goderbauer is the TL of the Flutter framework team. None of this talk would have been possible without thorough and patient explanations from them. Their genius is only exceeded by their kindness. There it is, folks. The life and times of a render object. Apparently I did this in 30 minutes. Is that real? I don't know if I reset the time at some point in the middle here. Anyway, Flutter only spends a few milliseconds doing this. Thank you, everybody.
Thank you, Craig.
Yeah.